Okay, hey, this is a little video for physics students learning about waves. This first video will be talking about some of the basic things as kind of introduction, overview of some of your basic ideas for all waves. One thing to be said about waves is that you may have seen waves in lots of different science classes, so you may already be familiar with some of these ideas from other classes. Waves are studied in all kinds of science areas. So here's a little outline of some of the things that will be covered. Here's a list of objectives, and this particular video is going to focus mainly on this first objective and then a little bit of an introduction to the second objective. And notice we just have a series of basically definitions and concepts, vocab, if you will. We'll go over most of these in the video, most of them shown in this first objective. So one of the most basic things would be, well, what is a wave? A wave is... So I have here an image which, it's a beautiful picture, right? But this would be probably what comes to mind if I said, hey, imagine a wave. So that's a wave in the ocean, obviously. But that's not the only kind of wave. So this is a really cool photograph, and this is a photograph of guitar strings. I would think that probably required a special camera to freeze that motion like that. And there are waves, there are actually two waves involved there. So there are waves in the string itself, like the guitar string is vibrating and that is a wave. But there's also what we hear. That's also involved. So the sound of the guitar would be a wave. Here's a picture of light. And if you look closely at this picture, there seems to be a wave-like thing. This is a laser beam shining through a special piece of plastic. Light is a type of wave. Here is just an image, just an artist rendering, I guess you could call it, of a special wave that was recently discovered. I guess it might have been 2000. It's been several years now, but this is a depiction of gravity waves. Gravity waves are this crazy idea that have been discovered, and gravity waves are very interesting. And that's one that if you ever have the time, you might try to hunt them down on the internet and look into that. It's pretty cool. Anyway, there are all kinds of waves. What do they all have in common? Well, here's how I would define waves. What is a wave? A wave is a disturbance that propagates through a medium. That's a pretty good definition. That would apply to all of the things that we were just looking at. The medium would be whatever it is that is being disturbed. For the ocean wave, let's just kind of use that one as an example. The ocean, the water itself is disturbed, and we can look at it and say, hey, the water's been disturbed. There's a wave. We know that it's disturbed because it's not in its equilibrium state. If you have water, a body of water at equilibrium, it's flat like a mirror, like a still lake that has no ripples. So when we say it's been disturbed, it's been changed from some sort of equilibrium state. And then we have a special word, propagate. Propagate implies that we have like a self-sustaining phenomenon. Once it gets started, it kind of has a life of its own. It's like a domino effect. Continues to reoccur throughout the medium. You can look out in the ocean and see a wave coming, and you know, okay, it's going to make it to me. If it's a big one, you better get out of the way or get ready to catch it if you're surfing. So propagation, the word propagation, if you look it up, one of the definitions is to reproduce. And a wave is reproduced as it goes along. The water near the shore is going to take on this shape of the wave that occurred in the water that was further out from shore. So that's an interesting idea. All waves have this property. One other thing that all waves have in common, and that's not really in my definition, but something that, all of the things shown on this slide are things that all waves have in common, whether it's the waves in the ocean or any of those other ones that I showed. All waves involve a transfer of energy. And there has to be some source. We have conservation of energy. If there's energy being transferred from something, well, it has to come from somewhere. It's going somewhere. The amount of energy doesn't really change. But a wave involves a movement of energy through the medium in all cases. I have here kind of a block diagram of that idea. All waves have a source and a medium. I get a disturbance that goes through the medium, but the medium itself is not traveling, right? It's not like the water at the ocean is coming up on the shore. It comes to the shore, it oscillates, but it doesn't pile up, right? It's not like the whole ocean is coming in. The disturbance is coming in. And to create that disturbance, we need some energy, and the source of that wave would supply whatever energy is being transported by the wave. For waves in the ocean, you might say that, okay, where's the source of the energy of those waves? Well, what determines where do the waves come from? Well, one of the big things is wind. Wind can generate waves, and the wind, the energy of the wind is put into the energy of the wave. The moon has an effect on waves, the tide. So there's a complex set of mechanisms by which this energy is created in the wave, and then the wave is carrying that energy. The ocean wave can do work. Energy is the ability to do work. So as the wave crashes on the beach, it might smash your sandcastle. Ah, man. All right. Now, while the wave is doing this, the medium itself is oscillating. So the water doesn't really go with the wave. The water moves. It's oscillating. It's moving back and forth or up and down or side to side, but it's not really coming in with the wave. There are several different types of waves, and we're going to look at that. So we're going to look at three kinds of waves: transverse, longitudinal, and surface. And there's also some terminology that goes with that. I have here a screenshot of a Desmos file that I set up that you can access. And you might want to stop the video or pause the video and play around with this. So how do you access this? There are two ways you could get to it. If you're familiar with my website, milliganphysics.com, there is a link to it in Physics 2 under the Waves and Interference section. So you could go there and click on that link, and it will open up Desmos for you. However, if you look at the top of the screenshot here, if you just type in that identifying number or code there, it will open this file that I created basically at Desmos. So it's not that hard to just type that in, or just go to Desmos and add that code onto the end of the URL for Desmos. But I think you would enjoy playing with this. And here's how to use it. You'll find some folders. If you click on the folder, you can turn on or off each type of the three waves that you're expected to know something about. So we have transverse waves, longitudinal waves, and the combination is basically what happens in a surface wave. You can also go slow motion or speed up or slow down the animation. You can change the parameters of the wave. So I would recommend that you go play with this and just kind of experiment with what you see there. A transverse wave is being illustrated here. So here I created a recording of what you would find on Desmos. And what we're looking at here is called a transverse wave. Look at the definition. The oscillation of the medium is perpendicular to the direction the wave travels. So I think you would agree with me that this wave is traveling from left to right. But the green bars are oscillating up and down. Up and down is perpendicular to left to right. And that's what makes this a transverse wave. This is a disturbance of the bars, the green bars. It's propagating through our medium. So this would be an illustration of a wave. We call this type of wave a transverse wave. I have kind of an illustration here. We have an oscillation, and we have a direction of travel, and those two things are perpendicular to one another. We have some sort of equilibrium, and then what we end up with is a pattern that's usually described as crests and troughs. So I bet you've heard those terms before. We get these humps or these valleys, and scientifically we usually refer to those as crests. A crest would be an upward or positive displacement. It's like the high point of the wave. Or troughs, and that would be a negative or downward displacement. It's like the low point in the wave. So we have crests and troughs whenever we have a transverse wave. And that's another way to think about it. So if it's a transverse wave, it's going to have crests and troughs and or troughs because of what's happening. That's probably the one that you would think of normally. If I just said, hey, what is a wave? And I asked you to draw a picture of a wave, you would probably draw a squiggly line like the one shown here. But there are some other things that can happen, and longitudinal waves are interesting. So what is a longitudinal wave? Well, I've got that here. And this may not be what you normally think of when you think of a wave, but this would be a wave because it is a disturbance propagating through a medium, and it has all the behavior of any other kind of wave. This kind of wave will do similar things. So yes, this is a wave. We have a different name for it because it's obviously kind of different what's happening. Notice the key difference in the definition is the word parallel. So basically, similar kind of definition, but replace the word perpendicular with parallel. Now the bars are perpendicular to the x-axis. Now I have them as purple bars. But what the bars are doing is moving left and right, and our wave is traveling to the right. And those two things are parallel. So that makes this a longitudinal wave. It's interesting to watch this one, you know. I'm going to turn on my little pointer here if I can. Oh, it's not going to let me do that. Oh, well, we'll just go forward. Oh, wait, here it is. No, it's not going to let me do that. It's okay. Anyway, it's an interesting pattern. And we get these regions where my bars are squished together and regions where they're further apart. But both of those regions were moving to the right in the animation. That's what I was going to point out. Anyway, we get a pattern that looks kind of like this. We have an oscillation, and we also have a direction of travel, and now those things are parallel. In my figure that I created here, I showed some bars equally spaced to represent equilibrium. So this time equilibrium is not like a level, but a regular spacing that might occur normally that has been disturbed by the presence of the wave. Now, what do we call these things? So these are not crests and troughs. Why not? They don't look like crests and troughs. They aren't crests and troughs. So these are some vocab words you might not be as familiar with, but a longitudinal wave has something analogous to crests and troughs. So what are we going to call them? Well, you could come up with some names, I'm sure, but what they're often called scientifically are the following two terms. Compressions are regions in the wave where the medium is squished together, basically, hence the word compress and compression. So if I use my pointer, this would be a compression right here. Notice my bars are closer together than they would be when there's no wave. So that's what we mean by compression. We also have these spaces where they're farther apart, less tightly spaced. So what are we going to call that? Well, that's a fun name. That's called a rarefaction, as in to rarefy, to make rare. Our particles of our medium are rarer, less densely packed. So I guess that's where the name comes from. Rarefaction is a fun vocab word. So I have a series of compressions and rarefaction. So if you look at this pattern, I have compression and then rarefaction and then compression and then rarefaction and so on. So taking the place of crests and troughs, we have compressions and rarefactions. The last type of wave we'll look at here is sometimes called a surface wave. So this is also something set up in the Desmos that you can play around with. And if we look at this pattern, it's pretty interesting. So notice my definition here is, well, it's occurring along a surface. This is really more accurately what's happening, waves in the ocean or waves on a lake. The surface of the ocean, the surface of the lake. The bars in my animation, I want you to take just a moment and just watch one single bar as the wave goes by. Keep your attention on one of the bars. If you watch one of the bars, what you notice is that it's moving left and right, but also up and down. And overall, it's moving in a sort of circular or oval path. So this is what's happening in a in a surface wave. We get some transverse action and some longitudinal action, and our medium is actually kind of looping around, which is fascinating. If you've ever been in the ocean, like just floating out on a wave, that seems right. That's what's going to happen if you're out on the ocean. You don't just go up and down. You kind of do this up and down and side to side when the wave goes by. The last thing in this video is just going to be some definitions of what are called wave parameters. So these are some things that you may have heard of before, but just that you could include in notes. Let's look at some definitions of common wave parameters. Parameters are the things that make a wave unique. So if we hear a particular sound, what is it about that sound that makes it a unique sound? Well, here are some things that might be describing a particular wave. So waves have a speed. The rate at which the disturbance is going through the medium is the speed of the wave, wave speed. The word speed is something you should be familiar with in physics. So how much distance per time, rate of change in distance per time for the disturbance. Now, one thing that makes this a little different is that we're not talking about an object moving at a certain speed. We're talking about a pattern of disturbance traveling at a certain speed. And that's the wave speed. Amplitude is a word that means how big, basically. How big is the problem? What's the amplitude of the problem? Well, for waves, it's the amplitude is how big is the disturbance. In physics, we typically measure amplitude from equilibrium. There are actually some different ways that you can define amplitude, but most often it would be the absolute most disturbance measured from equilibrium compared to the normal state when there was no wave. We often are interested in periodic motion when waves are involved. Waves often have a periodic aspect to them, so we might be interested in the period of the wave. We also might be interested in the frequency of the wave, and those are some definitions that would apply not just to waves, but anytime you use the words period and frequency. So hopefully you've seen those before. Frequency would often be measured in hertz, a special unit for frequency. And then the last thing is a quantity that is unique to waves. Everything before this, like those four definitions there, are things that could apply to other phenomena. So you can talk about the speed of a car. You're going to talk about the amplitude of a bouncing pendulum or a bounce mass on a spring. But the last one is wavelength, and that's a unique parameter describing waves. It's in the name, right? It's the length of the wave, wavelength. Wavelength is the length of a cycle. It's actually pretty similar to the concept of period, but now we're talking about distance for one cycle, basically. How long is a cycle in meters? And we always measure this in a line or along a line that's parallel to the direction that the wave is traveling. And that's called a wavelength. The last thing in this little video is a diagram illustrating these parameters. So if we go back to our sketch of a transverse wave, we can imagine it in motion. The speed would be the speed of the crests or the troughs if we were talking about a transverse wave. If it were a longitudinal wave, the speed of the wave is how rapidly the compressions are moving or how rapidly the rarefactions are moving. So we have to kind of imagine this pattern in motion for the speed. It is not how fast the particles are moving up and down, I should hasten to add. Amplitude would be the greatest amount that our medium is changed from equilibrium. So I showed it here as just how much down we went in this pattern. For this pattern, it would be symmetrical. You could also measure from equilibrium up. For a transverse wave, it would essentially be the size of the biggest crest or the size of the deepest trough. That would be called the amplitude. Frequency of a wave, number of oscillations per unit time. So again, we have to kind of use our minds to imagine it in motion. But as time goes on, of course, we would have this oscillation, and the number of oscillations per unit time would be the frequency of the wave pattern. The wavelength shows up nicely in the diagram. So wavelength, here's a visual for you. We have a special symbol for wavelength. The symbol for wavelength is the Greek letter lambda. Lambda looks like an upside down Y. It's essentially the Greek letter L. So it's kind of L for length, but it's a Greek letter for length. Anyway, lambda, that's a very standard symbol. Lambda would always represent wavelength when it comes to waves. And notice the way that it's shown here. It would be the linear distance from a crest to the next crest, and that would be one complete cycle in a simple pattern like this one, and that would be called the wavelength. We also have an equation that relates three of these variables. The speed of a wave is always equal to the frequency of the wave multiplied by the wavelength. Speed is distance per time, wavelength is the distance per one cycle, and frequency is the number of cycles per unit time. When I multiply, I get the distance per time, which is the speed of the wave. There's very much a logic to this, why that has to be true. It's essentially true not like it's a law of nature, it's just by the way we define things, it has to be true. Just by definition, this is a true statement by the way we define speed, by the way we define frequency, and by the way we define wavelength. This has to always be true. So that's a very important formula. You're going to get lots of practice and experience using that formula in this unit. I hope this video has been helpful to introduce you to some of the basic terminology for waves, but that's going to do it for now, so I'll see you next time.